So next we have Laura Prichard, spectroscopy confirmation of escaping ionizing flux from individual high-redshift galaxies.
Okay, can you see and hear me okay?
Yeah, Laura, please go ahead.
Hi, thank you so much to the organisers for putting on a great conference, and also to the other speakers for their excellent talks and beautiful slides. I've learned a lot this week. I'm Laura Prichard. I'm a postdoc at the Space Telescope Science Institute. I work with Mark Rafalski there and Jeff Cookie and others at Swinburne in Melbourne. This project focuses on the identification of galaxies like these that emit ionizing UV radiation. These high redshift star-forming galaxies likely played the biggest role in cosmic reionization, transforming it from neutral to almost completely ionized at redshifts greater than 6. In this figure, you see a central star-forming galaxy outflowing ionizing radiation and neutral clouds of material that surround the galaxy. Any ionizing photon that escapes from the galaxy is often called a Lyman Continuum photon because it's emitted at far ultraviolet wavelengths below the Lyman Break, which is at 912 angstroms. These ionizing photons are rapidly hoovered up by any neutral material, and as such, at redshifts greater than 5, the intergalactic medium in the universe was so dense that it actually acts as an opaque veil to this radiation, which obscures our view of cosmic reionization. So while we can't look back to cosmic reionization itself, we can look back to galaxies very close in time and properties between a redshift of 3 and 5. However, this is not an easy task. First, the ionizing photon has to escape the galaxy itself. It then has to travel across most of the age of the universe without coming into contact with any neutral material until we can observe it at Earth. So while these are our best hope of placing observational constraints on cosmic reionization, this is an incredibly elusive population of galaxies that poses many observational challenges. And there has been a string of bad luck or false or not widely accepted detections as a result. As such, to date, there are still only a handful of individual spectroscopic Lyman Continuum detections from galaxies. So how do we go about searching for these Lyman Continuum galaxies? This plot shows a standard Lyman Break galaxy spectrum. This is a typical high redshift star-forming galaxy spectrum. And you can see it shows the signature Lyman Break below 912 angstroms, where all the ionizing photons are absorbed. It has strong Lyman alpha emission, and it also has a Barmer break around 4,000 angstroms. Overlaid over the top are photometric bands. These are actually the Hubble Space Telescope bands used in the CANDLE survey, and they span from rest far ultraviolet through to near infrared wavelengths. An incredibly powerful technique for getting redshifts for distant galaxies is something called the Lyman Break technique. Instead of relying on observationally expensive spectroscopy, you can instead rely on multi-band images to find distant galaxies at these high redshifts. So in this video, you'll see the spectrum moving with redshift, and we'll zoom in on galaxies that fall out of these bands. As we go to higher redshifts, the Lyman limit moves, and the bands that the galaxies drop out of allows us to get approximate redshifts for the galaxies. This is the powerful principle behind the Lyman Break technique, and it's led to the discovery of the highest redshift galaxies that we know about. The bands shown in the video are the Hubble bands F275W, F336W, and F435W. So with these bands, you can cleanly span below the Lyman limit at redshifts greater than 2.4, 3.1, and 4.4 respectively. Therefore, with these bands, you can span these crucial redshifts that lead you up to this observable limit of the far ultraviolet at redshifts of 5. An important question to ask, though, is if you add flux to the spectrum below the Lyman Break, is it always identifiable as a Lyman Break galaxy? In other words, do Lyman Break galaxy selections sometimes miss Lyman Continuum galaxies? To identify a Lyman Continuum galaxy, you need 2 bits of information. You need the redshift and a method of measuring leaking Lyman Continuum flux. So one way to really test this is to identify a population of distant galaxies without relying on the Lyman Break technique for their redshifts. My collaborator, Joris Mestrick, recently published a comprehensive search of spectroscopic redshifts in the cosmos field, so without relying on the Lyman Break technique, although it's important to note that often spectroscopic redshifts have biases themselves. Targets are often pre-selected with the Lyman Break technique. With Cloud's U-band imaging, which is ground-based to detect leaking Lyman continuum flux, and optical high-resolution HST imaging for finding low redshift contaminants, SAZERAC was actually able to identify 2 new Lyman continuum galaxies and 3 promising candidates using this more agnostic approach. In this work, to identify a population of Lyman continuum galaxies in a less biased way, we've again targeted the cosmos field. Cosmos is covered by 30 band imaging, including deep, medium, IR, 4-star bands, and these were used in the ZFOURGE survey for determining photometric redshifts. ZFOURGE is the ideal survey for this, as these medium bands actually span the Lyman Break, as you can see in the image on the right, rather than relying on the Lyman Break that these galaxies may not have. This results in very accurate redshifts, errors less than 2%, and minimal catastrophic errors. So we have a field and a method of accurate redshifts. All that's needed is the efficient detection of leaking Lyman continuum flux. For this, we have deep HST images that probe this, the rest FUV at redshifts greater than 3.1 and 4.4 for F336W and F435W respectively. You can see these 4 untargeted pointings in the large cosmos footprint on the left. We're in the regime that every pixel counts to identify these often very faint ionizing sources. And for that reason, I've made several improvements to the Wide Field Camera 3 UVIS reduction pipeline to clean these images up far beyond what's publicly available from MAST. So I'll mostly let the images speak for themselves and just touch on a few of the main highlights of my new reduction pipeline, but please reach out to me via Slack or email if you would like to clean up your Wide Field Camera 3 UVIS images. All of the codes for this are public, and I'll be happy to help. I'm part of the UV Candles collaboration and run all the custom reductions for that survey. So here's an example of my improvements that were used by another program. This is a nearby spiral galaxy. The MAST image is shown on the left, and the image with my custom calibrations is shown on the right. You'll see that there are gradients and also offsets between 4 quadrants, which are smoothed out. And on the pixel level, there are divots and also blotchy patterns that are caused by poor quality darks that make identifying faint objects very challenging. And this has all been resolved in my new custom reduction. So these improvements have taken a long time, a lot of work and testing, and is usually the way with data reduction. People usually don't want to hear about the details. So luckily for you, Space Telescope is actually now implementing all of my improvements to the darks pipeline as standard. Therefore, much improved reduced data will be available for download directly from MAST soon. But for help applying any additional corrections, please do get in touch. So back to the science, myself and my collaborators visually inspected all 400 objects in the newly reduced images that were the redshift range such that they would pick up ionizing radiation. The high resolution of the HST images helps us to identify any low redshift contaminants. So did this less biased approach actually work for identifying Lyman continuum galaxies? Here's one of our Lyman continuum candidates. Here I'm showing the same galaxy in three different wavelengths in these 3 images. So we've got the far ultraviolet on the left, where you can actually see some leaking Lyman continuum flux, through to optical and near infrared on the right. However, to truly determine the nature of these targets, we have to get spectroscopic follow-up to confirm their ZFOURGE redshifts. And in January of this year, we got Keck LRIS spectroscopy for some of our Lyman continuum candidates, and I'll show you some of those exciting preliminary results today. So here I'm just smoothing the HST image to make that Lyman continuum image a bit clearer. The LRIS spectrum here is shown in gray. There's a Lyman Break galaxy stack spectrum, which is shown over the top in blue, and the yellow show positions of skylines where the flux should be ignored. This galaxy was spectroscopically confirmed at redshift 4.37, so very close to the ZFOURGE redshift, with emission and absorption features as shown. As you can see in the Lyman Break galaxy stack, there's actually no flux bluewood of the Lyman limit, and this in our LRIS spectrum, you can see that there is leaking Lyman continuum flux for this galaxy. Here's another one of our targets. This is a redshift 4.48 that was confirmed. So again, if we just smooth the Lyman continuum image, it becomes a bit clearer. Here I'm showing just the red side of the spectrum. We're still working on reducing the blue side. The red end of the spectrum, however, still allows us to get a redshift for this galaxy, confirming that the flux that we see in the HST image is genuine leaking Lyman continuum flux. So from our photometric search, we found 8 good quality candidates and 12 others, and this represents a 5% detection rate in the F336W images, which is significant. And from our spectroscopic follow-up, we're able to confirm 4 new individual Lyman Continuum galaxies in just those 4 untargeted pointings in the cosmos field. The work presented today serves as a successful pilot study for the method, but I should emphasize that this work is incredibly challenging. It requires both deep UV HST imaging and ground-based spectroscopy. The UV Candle Survey is a vast HST program that will provide UV coverage of 4 of the 5 candles fields, and it's over 98% complete already. While these images are shallower than our pilot, the area covered is 10 times larger. Our pilot study has shown that spectroscopic follow-up is essential to confirm the selected targets that we find in the photometry. And I was recently awarded 1.5 nights of NASA Keck time to follow up photometrically selected UV candles targets in cosmos. And our estimates show that we could get tens of spectroscopic confirmations. This method provides a way to identify Lyman Continuum galaxies at redshifts where we can actually observe the ionizing flux leaking. We can therefore build up a statistically significant sample of Lyman Continuum leakers in order to observationally constrain cosmic reionization. And I'll just leave it there with my future work. Thanks so much.
All right, questions. Okay, so a few questions come in Slack. First, Harry Ferguson asked, do you have estimates of the Lyman Continuum escape fraction for the galaxies you detect, correcting for IGM attenuation?
We'll be getting those at the moment. So as I mentioned briefly, the work on the images has taken a long time. And for anyone who's worked in the UV in photometry knows that UV photometry can be very challenging. For example, getting PSFs and also knowing what isotopes to extract the flux from. So that's all being done kind of in parallel with UV candles, but I'm looking forward to really being able to hone in on the escape fractions. Some preliminary results show that it could be between 5 and 10% for our targets, but those are not well fleshed out. But we have simulations for proper treatment of the IGM attenuation, for example. So we're gonna give them a proper estimate.
The next question is sort of related. Rohan asked, how transparent must IGM sideline be at redshift 4.8 for detect limit limit for the source? Based on the simulation, it should be pretty opaque.
Great question. From Joros Mestrik's work, actually, he found that you really have to have the most transparent lines through the IGM in order to be able to detect these galaxies. So that further complicates inferring physical properties from the Lyman Continuum galaxies that we detect, because we're biased to the cleanest lines of sight. But it's something that I'll be looking at with this sample, but certainly we're biased towards the ones that we can see the clearest.
Thanks. Next question is about, can you rule out AGN activities in the leakers?
We'll be cross-referencing with all AGN catalogs, but certainly for these galaxies, I'm pretty sure these don't have AGN in them, but I need to double check. But yeah, we'll definitely be cross-referencing all catalogs to make sure these are genuine detections of leaking Lyman Continuum flux from galaxies rather than AGN.
All right, thanks. Next question is the surface brightness you see in the Lyman Continuum image consistent with being smooth given the signal noise, or do you require the leak emission to be patchy?
It's an interesting question. Each of these sources is incredibly different. So sometimes the emission comes, it looks patchy, sometimes it looks offset, sometimes it looks very compact and centered really on the galaxy. So it's definitely a diverse collection, and we'll be looking into the morphology of these sources for sure.